This is our last seminar in this semester, and let me first make some organizational announcements. We will have an exam in the next Thursday and Friday, and today or maybe tomorrow I will send you problems to solve, and you have some time to solve them at home, and then you will arrange discussions of the problem with us. So each of the speakers will discuss problems on his part of the course, and the method how to fix a time slot for you will be also announced in my email. I will send my email to everyone who was filled in the form on mat-net on this seminar, as well as everyone who is registered as a as a seminar participant at a mathematical department of HSE. So both of these categories will receive the problems, and hence they can discuss them next week. If you want to also have these problems and you are not in any of these two categories, you can just write to me and I'll send you problems also. So this is the procedure, and we assume that to get an excellent mark, you should, it is most probable that for every part there will be 2 problems, and excellent mark will be most probably 4 problems of 6 total. Okay, so let us now pass to the mathematics, and let me recall. Okay, so you can. Okay, so today we will. So let me recall what we have discussed last time. We have discussed that for some smooth systems we have so-called hyperbolic systems, and for them there is some sort of Markov. They look the same as the Markov chains in some sense. I didn't present the exact statement, but loosely speaking, you just somehow relate a topological Markov chain to the to this hyperbolic system, and so to have say to study some limit theorems for this smooth system, you can as well study this limit theorem for the Markov chains. However, there is some yes, and last time we have discussed the following, that these smooth systems have many invariant measures and even many ergodic measures, and it is not clear which measure to choose. However, I have stated last time that there is one measure that has the measure of maximal entropy. that somehow grasps the behavior of the systems, the chaoticity of this system best of all. And this measure is, in this case, Markov. And this is a so-called Perry measure, and we have discussed last time what it is. So we have this smooth system. So we have some x, t, and this measure mu, and we have an isometry, isomorphism to some Markov chain. So we have some sigma with a shift and with a Markov measure. So this is an isometry. So this is, say, an also system. With measure of maximal entropy, and this is a Markov chain. So then we should take some function, consider the averaging of this function along the trajectory. So you take f of x plus, well, let's say f belongs to some nice free space, nice functional space, say L2 of xt, of x mu. Then you take an ergodic average. But you divide it, so let us assume that this measure had a zero average. Otherwise, I should subtract it. So this means that the integral of f d mu equals 0. Then I can divide this. So if I divide this by n, then by an ergodic theorem, this tends to 0 in L2 and almost surely, so in any required way. But if I divide this by square root of n, then this resembles the limit theorem. And we have that we have this equals to, well, to what? To, we should, we can take this isometry. So we take the corresponding function here. And so we have g of some omega plus g of sigma to the n-1 of omega by square root of n. And here g is in L2 not of. So we can shift our discussion of, we can translate the discussion of limit theorems from the smooth system to the Markov chain. Then, however, we have some detail which I want to discuss now. We will discuss this Markov chain for the we'll discuss the limit theorem for Markov chain in a more restrictive way. And this is a more natural thing. So let us assume that H belongs to L2 node of the alphabet, well, let's say A, and the stationary distribution. So this is a set of, or maybe let me write it down as S. This is a set of states. And this is a stationary distribution. Well, in our case, when we have just when this set is just a finite set with some measure, of course, it is not too interesting to say that it belongs to L2. Every function belongs to L2. But in fact, this can be generalized to more general sets of states, so countable or even uncountable. This is in fact quite general citation. But I want to stress that these functions are not are much more restrictive than the general case, than this case. So why is it so? Because you can just and then if you have such function, then you can say that h omega equals to h of omega naught. So you just look at the function of the zeroth coordinate, and then you can arrange the same thing of omega you can write this like this, or which is the same as h of omega naught plus h of omega n to n minus 1. So then we can say that the limit theorem is just that you take the value, the current state of your Markov chain, and then you consider some number corresponding to this state, the number h of the state. And then you consider this sum divided by square root of n. Of course, this is much more restrictive situation than the general function g. However, I have sketched last time that if you have, that the general situation can be approximated by this. To do this, we should start with the functions that depends only on finitely many omegas. So assume the next step that we have h of, say, omega naught. So h, assume that our function depends only on finitely many, well, let's say it omega k minus 1, of only finitely many elements of our sequence. Then it is quite natural to say that our function on the whole, that depends on the whole sequence, can be somehow approximated by such functions. Well, of course, there is a discussion in one way, in what sense it is approximated. In fact, and this is entirely out of my what I want to discuss precisely. When you have a sufficiently regular function on your smooth space, then the corresponding function of on a Markov chain is very good, very well approximated by the functions of such sort. And for functions of such sort, you have a convergence of in fact, this is also a functions on a Markov chain. This is a standard construction. If you have a Markov chain, you can then, so you have some Markov chain, and you have this shift, and you have a shift map and a measure, and then you can consider a new set. You can say s to the k to the z, and you have a map here, which is as follows. So the sequence omega maps to the sequence, well, let's say alpha, where alpha n is just omega n plus k minus 1. Just like this. So you just then, of course, this is again a Markov chain. Because you can see that when you know alpha n, then you have only as many alpha n plus 1 as you. So first of all, they should coincide on this. They should agree on the common part of this words. But also, if you want, you can say that what are the transitional probabilities. Transitional probability is a probability to go from omega. So if you want to say what is the probability of, well, let's see, alpha n equals to some psi n blah blah blah, alpha n plus s equals to psi s. Well, this is a probability that omega from n to n plus k minus 1 equals to psi n, and then omega, let's see, n plus k equals psi n plus 1. Let's write it like this: k minus 1 and so on up to omega n plus k plus s minus 1 equals to psi s k minus 1. Something like this, n plus s. And then you can see that this number can, of course, assuming that psi n's agree with each other on this common k minus 1 words. So, and then you just have the Markov measure. It is an exercise. So if you have a convergence of these things to some in distribution to the normal distribution, then you have the same for the functions that depends only on finitely many elements. And then you should somehow interchange these two limits. These two limits. One limit when you approximate your function, and another limit when you push n to infinity, and so you take to the normal limit. And this is also quite complicated thing, but again, I have no time to discuss it. So today we will discuss only this first step, this most elementary step, which is this statement. That for a Markov chain, we have this convergence. Then I want to say that this is more or less a standard. This is of course something that resembles a Markov chain, resembles a standard central limit theorem for an independent variable very well. However, we have some difficulties. The difficulties are how one can prove this standard central limit theorem. You just take the characteristic function, and then you see that it tends to what you want, to the exponent. And also there is a question, what is sigma square here? Because until now we have no idea about this. In the independent case, this is trivial. This is just the variance of h, but in this case, the situation is more complicated. So let me discuss this this result. So theorem assume that the Markov sigma. Well, let's write it down as P is a Markov chain such that we need some conditions. So this Markov chain. So for this Markov chain, let us define the set of states, transitional probability matrix, and stationary distribution. So there is some part which that we will fill in later. That is, we have some assumptions on. So let me write down that S is less than infinity. So we just discuss the finite case. But of course, this also can be extended. Then we take a function phi. Well, let me say that it is from here. But of course, in a finite case, this is just say that there is any function with zero average. So that the sum of pi f of I over I s equals 0. Okay, then we take these sums. We have omega naught plus and this tends to in distribution to some Gaussian distribution. So what are the conditions on our Markov chain? Assume that our Markov chain, for example, is very predictable, that there are just two states and you go from one state to the other with a probability 1. Then it is clear that your sum is just it has just two there are just two variants. So if you have this Markov chain, and so we have some function. So first of all, the stationary distribution is 1/2, 1/2. And therefore, when you consider a function, you have some value f0 here and some value f1 here. And then when you write down this sum, you have, well, formally speaking, you have this this convergence, but in a very in not so interesting situation. So you have just so your sum is, so let's say this is psi n, which is and this is in fact minus f0. So it is f0 minus f0 plus blah 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 divided by square root of n, and so it ends with this with probability equal to 1/2 and minus the same. So we start with minus f0 plus f0 blah 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 with probability 1/2. And therefore, this is just plus or minus this with probability 1/2. And of course, there is no, so of course, this tends to 0 in distribution, to just the constant 0. So it seems that this is a case of the case when just sigma square equals 0. So in fact, it works here. But let us assume for this is convenient, a convenient thing that we have some power such that all elements are positive. So this means that there exists some I such that for all k and l, pi to the I k l is positive. So this means that in I steps we can go from any state to any other state. So this is the statement of the theorem. So let us try to write down the same characteristic functions as usual. So we have expectation of this. So we have that this equals to the following, that this is an exponent of, well, of course we can write it down like this. But for the independent random variables, we can say that we can split this into separate functions because these functions are independent, so we can split this into a product of these, so divided by square root of n. So we can split this into the product of expectations, and then for one step we have this, that this function is just 1 plus something small, and then we just study one function, and then we have something like I don't remember exactly what, but this is something like sigma f n, and then you just take the power of n. This goes like this. Well, of course there is some next terms, some approximations, but it goes like this. And then so we have this exponent. So this is well, maybe there is 2 here. So this is e to the minus lambda square sigma f, well, x square divided by 2. This goes to, and this is a proof for the independent IIT. Well, what will change for the Markov chains? For the Markov chains, we have no such independence. However, when you look at the elements that are quite far away from each other, then we have an independence, this independence. So we can take the elements that are quite distant, and then they are almost independent. Well, let's call it lemma. Take an expectation, say, of some function g of omega n, h of naught. Then this goes to, well, again, gh belongs to L to naught. Then this goes to 0 exponentially fast. How to prove this? Are there any ideas? Well, in fact, this lemma is quite straightforward. If you consider the, say, vector g, so what is this? This is a probability. So this is a sum over O, I, and j. That probability that g that omega n equals j, that omega naught equals I, times the, well, G of J and E H of I. And this is what? This is a pi I times pi to the n ij. And so the whole thing is the following. I can say that this is well, let's write it down like this. So let's call this. So here, so pH is a vector whose components are just the pi g hi h of I, and the same. And for g, we have just gi equals to g. And so you have just this. And this, of course, so we know what to do with this. G is a in our assumption, all so the spectrum. Well, or I can say that the Jordan normal form of the function pi, it looks like this. This is one that corresponds to the stationary distribution, and there are some j. Let's say k lambda, and here all here absolute values of lambda is less than 1. And of course, as there are finitely many of them, then we can say that they all smaller than some number that is smaller than 1. And then if you take the powers of this matrix, then the power will grow. So it will put. So there is so pi n. Then you can say that pi n of let me see, of any vector tends to the projection of this vector to this one. Well, of course, this projection is a bit tricky because when you're in a linear situation, it is not sufficient to say what means the projection. Well, the projection means that the projection along all the other elements here. But nevertheless, let us say yes, and but in fact, this projection is quite easy to establish because the projection is just so P1 of omega is just the sum of omega I times P. No, I'm sorry. No. Well, this is also true, but not. But there is some difficulty. So what do we know? That this matrix converges to the matrix P. To the matrix of stationary distributions. So the probability going from I to J became the conditional probability. it will not depend on I. So it is just the vector that is. So we have this P1, Pn, P1, Pn, so on P1, Pn. So this the ij element is just tends to pi j. So when we it seems that there is, well, okay. And then we have that this thing is the following. You just take a pi. So here we have the sum for I and j. Pi I h of I times pi j g of j. So this times here. So this is even not needed, I'm sorry. So I know this, and then for the limit of this thing, as n goes to infinity, you have this. But here, this equals 0, the sum over I, and the sum over j is also 0, so it is 0. And that's it. So we have seen that we have we see that the limit is 0. And then you can also see that the convergence to this limit is asymptotically is exponential in asymptotics. Why is it so? Because this convergence is so if you take the difference, then this difference is not more than q, some constant q to the n, q naught to the n. Because if you take a Jordan normal form and then go take its exponent, take its powers, then you have the convergence to this matrix. So j pi to the n, convergence to 1 and so 0 everywhere else. And the difference is, of course, estimated by c, well, maybe not q naught, but well, any q to the n where q is larger than q naught. Because so here you have that this is not more than some c m to the dq naught to the n, and this can be estimated with cq to the n. So you have this exponential convergence, and then when you change the basis, you have the same conversion because this change is just a linear change of coordinates. Therefore, you have this thing that we have this exponential convergence. So the correlations decay exponentially if you consider the covariance of f of say g of omega n and h of omega naught, then this decay goes to 0 exponentially fast. This is such a statement is usually called the decay of correlations, when in this situation it is exponential. So the idea again is that when you know something about first about some states near 0, then for the large omega n you know nothing, in fact. And this is just the more quantitative approach to this statement. Well, let me now let me try to discuss what will happen when you consider the same thing here. Well, let me do the same, but now we have this problem that we cannot go to the products. So we have the characteristic E, so expectation of well, so we have seen that this is this. We see that each term is, of course, this is a characteristic function of. You see that these exponents are, in fact, of small number, because f are, in our case, even bounded, and so you take this exponent of something that is small, and so you can write it down like this. This is an expectation of the product of 1 plus r lambda. And plus well, let us write it down like O large of 1 over n to 2/3. And this O large is, in fact, it can be just bounded by some constant that does not depend on, well, it depends on lambda, but it doesn't depend on the values of our omega g. Now, if I take this product, I'll have, I can just consider this product, multiply everything, and then I can say that I have, if I choose one of my brackets. So first of all, each of these, of course, is O large of 1. Now, let me now do the following. If I take this product and even in one term, I take this. Then when I multiply this by all by the product of all the rest of the brackets of the multipliers, I have, of course, the same O large of this, because the rest is O large of 1. Well, to be precise, I can even say that well, that this is not enough for me, because of course I need more. I want to say that the logarithm of this, so that this is O large of 1 over square root of n. And therefore, when I take this product, well, in fact, well, and also J does not equal to sum J naught. Then each term, so O large means some universal constant, say million. Then if you can say that this is an exponent of the sum of, again, over the same thing, 1 over 1 plus of the logarithms. So the logarithms are just O large of 1 over square root of n. There are n terms, and so the whole thing is something of O large of, just a moment. Well, okay, so let me write it down more precisely. Okay. Well, maybe I should also take the, I'm sorry, let us also take the logarithms. So this is an expectation of the exponent of the sum of the logarithms. If I take the logarithms, I take I lambda first. I have just this. And the next term in the expansion of the logarithm, so I take the logarithm of 1 plus z equals z plus what? Minus z square over 2 plus and so on, right? So I take from the next term is goes here, but this term is still works, and it yields well. Let me write it down. This yields minus the square of this, so plus lambda square to n f square of omega j. Well, plus or small of 1 over n to the 2/3. Then let me. So now I can sum everything inside this exponent. So I have exponent of the sum of f of omega j's. Well, this term. I'm sorry. So there should be some silly typo. Oh, I'm sorry. Here is f square. And so, of course, so no, I think I should still try to. So the idea is to eliminate everything except for the most important terms. So the terms that and say that everything else is negligible, exactly as in our situation with in our situation for the independent variables. Okay, so let me try this again. So if I consider this product of this term times everything else from the other terms. So I take this term. So it is, well, let's say this is, so I take all small of 1 over n to 2/3. So this is from j equals to g naught. And then you have this product. As I have said, each term is small, and moreover, so I want to say that this the whole thing is of because it is not only small, but it is it has so this number has 0 belongs to IR, so it is it's just imaginary. So the exponent has 0 has an absolute value of 1. So the whole thing can be estimated again by all at the same. And so these terms together all large of this times this product yields n times all large of 1 over n thirds. So this goes to 0. So the first step was to eliminate all these terms. Now I have just this product, the product of 1 minus I lambda square root of n f of omega I plus no, here is and everything else goes to 0, so it's not important. Now here again, I would like to say that if I take a term which is not so the idea is simple. There are many terms that have too large power of n in the denominator, and I want to, the power that is larger than n, and I want to say that all these terms are again negligible. So if you take the product of if you take from some, well, there are several sorts of this. You, for example, you can take these terms from 3 different multipliers, and then you multiply this by the rest. Of course, to be precise, I multiply now these numbers, and here let me just say that these numbers are still close to is still by absolute value very close to so the absolute value of this thing is equals to 1 plus all large of 1 over n to 2/3. So again, when I choose these elements from 3 from some, so if I choose this term from say 3 multipliers, and then you multiply this by the rest, then again the product of the rest is almost 1 by absolute value, and these terms yields 1 over n to 2/3. The number of, so each individual such product yields all large of 1 over n to 2/3, but the number of such choices is too large, is too small, because each of them is yes, so you have that this this term is so we have like this expectation of f of, so the whole term is something like 1 over n to the third by some constant, and then multiplied by the choice of the elements. There are to choose 3 is I'm sorry, it is n cube. So maybe I again have some difficulty. Well, maybe I should use it even now. So now let me try to write down everything. So if you take this product, you see that if you take if you take 2 of them, okay, so first of all, I will have so this 1 minus plus this. Let us first write down what is so the expectation of all this thing plus minus the sum of lambda square over 2n of this. Then I'll have the sum of, again, minus lambda square to n f of omega I, f of omega j, and here you have I is, say, less than j. And also I should take yes, that's it. And any other term is just too small. At least, so I want to say that all the other terms yields negligible are negligible in this product when you take to go to expectations and so on. Well, this is because of the following. If you take so consider such term, then if you take too many, let's say this, too many of these, you have a very small numerator, and then when you consider the expectation, well, let us again consider these terms. So it is something like the expectation of the sum over all I less than j less than k of something like 1 over n to 2/3, and then f of omega I, f of omega j, f of omega k. I want to say that this thing is small. Of course, the stupid argument that says that, of course, each term is bounded, and so does not work, because you see that the sum is something like m cubed over 6 terms. Yes, but I want to do the following. If the numbers are quite close to each other, well, let's say if if j minus I by absolute value is less than some d, then there are, and let's say this is also small, then there are something like n times d square such terms. And therefore, these terms are not too important, because there are a few of them. On the other hand, so if, well, let's say k minus j is larger than some d, then this expectation of f of omega I, f of omega j, f of omega k is exponentially close to, well, let's start with some, it's just this. We can say that this is approximately the expectation of this function times the expectation of this function. Because one function depends on two indices here, and another depends on one index which is quite far away. This is not exactly this what I have stated before, but the proof is the same, in fact. This is a so-called mixing, in fact. And so here this is just 0, and that's it. Therefore, so to do this precisely, you should just state that this this thing is something like, so we have some q to the d. Yes, so by absolute value, this is something like this. But this q to the d, so if you sum over d, then this is still negligible. So of course you first need to multiply, you have to count the numbers. You have to multiply it by the number of such terms, but n cube times to the q to the d. If d is sufficiently large, then this is small. So first you say that you take d sufficiently large. You can say that, well, in fact, you just have something like the sum. You have just all triples, and the weight of each triple is the exponent of the largest gap. And you need to say that the sum of this, the exponent with where the q is less than 1. And you want to estimate this and prove that when you take that over the entire cube, then this is something bounded. Well, maybe grows like something like n. And this is of course true, because you can say that on the plane, so if you fix one element, say j, then for the others you have this exponential decay. And so this is an exercise to prove that you have that this sum goes to 0. The main mechanism I presented here, but the details may be a bit tricky to follow in all details. Okay, and in fact, the same holds for any other term. So if you take, for example, because of course you can do the same when you multiply this by other function. So you can, for example, see you can do the following. You can, if you take some other terms, so you need to multiply this by, for example, some other brackets, just as before, by the products of all these things. Well, over some s does not equal to I, j, and k. And then you need again to estimate, to say that this function is on the one hand very close to 1, and therefore it cannot change the expected value too much. And we see that this expected value is in fact almost 0. And so that when you multiply it by this product, then you can see that it is not, it cannot be disturbed too much, because it is important to say that that here well, of course, in general, this is not true, because if you say take a random variable such that it is -1 here and 1, well, some say minus n here and n here, then its expected value is 0. Or if you, but if you multiply it by a function that is close to some, say equal to 1 here, but quite close to 1 here, say 1 + 1 over n, then the expected value of this product can be quite large. It can be changed quite a bit. But if you look more carefully at this procedure, you see that the only thing you should bother is this term. And this term, of course, you can, and for this term, you again can make the same argument, that the terms on the fixed distance, there are not too much of them, something like t, and they bring not too much to this expected value, because f is bounded, and you can take, say, different, you can take separately f plus and f minus. Each of them is not changed too much, so it is bounded, and so on. And the remaining terms are also close to 1 and also almost independent of omega k. So by this argument, we have this, that we can say that the plus tends to just this. Well, in fact, I have missed this. No. So no, just a moment. So I want to say that this goes to what? Well, to the following thing. Just a moment. So it takes this. I have missed exponents somewhere. Okay. Let's continue our this thing. So maybe I should well, the trouble is that, of course, if you consider just one term, then it is true that you, for example, you take the products of three of these and three of these terms and everything else from the remaining. But I guess that I am I said something too strong here when I expand this product. I want to say that the following is true. So let us look at this a bit more. Just a moment. Okay, so let me do this as follows. I have this product, and maybe I should write it down in a different way. So we have seen that these terms are negligible. I want to say that this no. Well, okay. I think I can explain this as follows. You have this product, and you want to discover what it is. Let me say that for a function so in fact what has been done here is in fact the following calculation. We have seen that these terms are exactly ones that generated by the expected value and the variance. You see that this term. So if you be just so if you calculate this just naively, then you see that this goes to 0. And as for remaining, the same, almost the same is true. So here you have just, for example, here you can, again, you have just a sum, and so this yields just the variance of f times something like lambda to the square root of 2n, divided by n to n. This term is a bit more delicate, and it is something like this. You can say that this is a covariance of f omega I and f omega j, and of course this is shift invariant. So you can say that here you take so you can say that so here is this product, and for if I minus j is constant, then you have the same expectation. This is just the expected value of f of omega naught and f of omega j minus I, because our distribution is shift invariant. What is how many of each of these are present here? Well, each of these, well, there are first of them are with are almost there are almost n of them, n minus something, and then this product, this and this expectation goes to infinity to 0 exponentially fast. Therefore, and this 1 over n says that so we have here we have some say C and K expectations of f omega naught f omega k k the sum from k equals 1 to n, and C and K goes to 1 when n goes to infinity, and this thing goes to 0 exponentially, and therefore the whole thing approaches just the sum of these values. Well, and because the first terms, so if you take the first some fixed number of terms, then you have this tendency, and the remaining part of the sum is uniformly small. So these are, in fact, what has been done here. We have discovered what is sigma f. In fact, our sigma f squared is just variance of f plus, I guess I missed 2 here. Well, it is like this. This is the formula for sigma f. Well, it was not a proof, but somehow we figured out from this calculation what are the most important terms in this formula. Now I want to prove that that this formula, that this expectation goes to e to the minus lambda square sigma f squared over 2. And to do this, well, the problem is that it is not true that for each term we have this. Yes. So because now it appears a stupid version of this, that because this takes just the quadratic term, what I have seen here. But this means that some of these remaining terms also have non-zero limit, and so they should be accounted for. Well, and how to do this? There can be. So maybe we should do this. Well, we should take these exponents and take some uniform expectations. So of course you can, so this is an estimate, but you can, so maybe I will try to do this, but so I'm sorry, I'm out of what I was prepared because there was a mistake here. So we have this product. Then we can decompose it and say that this is the products of all G1 and 2Gn, and then we have these things. So I lambda to the square root of n to the n, and then it is a product of to the n by the sum of no. So I just take this. Well, let's see it like this. we can write it down like this. And then I have seen that about the important terms here. So everything else goes to 0, but there are some of them that are important. And the first group of important terms is when, well, if I take just one term, so I have all kj's equals 0, and just one of them equals something. Then I yield just an exponent of lambda over square root of n. No. Sorry. True. Well, I have to prove that if I take, so I can consider this sum, and also I can consider this sum. So it is just lambda sigma to sigma f. And that's it. Sigma f squared divided by n. And I can compare these two terms. And in fact, what I have done was that the terms with lambda with k equals. So k is just the power of lambda. Well, if k equals 0, then you have just 1 equals 1. If k equals 1, then you have the expectations of f omega j's, which is 0. So again, we have an agreement. And then we have f equal, we have k equal 2. And this was our definition of sigma f squared. And then there are larger terms. And I want to say that these larger terms are yield just this. And from the probabilistic point of view, this means that if you take the same approach to each such term and to expectations, then you can approximate the expectation of this product of f omega j's with to account for only one effect, which means that for small difference you have this decay, and for large you have just you have this product. So we have some product of f omega. Well, you have say omega j1, f omega j2, blah blah blah, f omega jk. And you want to say that this product can be approximated as follows: that if again, if the difference is large, then if some of the difference is large, then it is negligible, and for small differences, it is so there is a term. For example, let's say that omega equals, let's say 3. Here is lambda square. Yes. I want to say that there is for example, for 4 points, we have some special terms. So not we cannot just say that. There is some balance, in fact. So, well, let's say k equals 4. Then you have this. Well, let's again say that omega 1 less than omega g2. So just g1 less than g2, less than g3, less than g4. Well, what are the terms? What are important in our formula? Well, we observe this. There are terms such that we have all omegas quite close to each other. Then you have such a product, but then the number of such terms is very small. If, for example, then, for example, 3 terms, so the number of such is something like of the order of n. And you multiply this by 1 over n squared. Yes, 1 over square root of n to the 4. So this is negligible. Then 3 together, 1 out. Again, the number of such terms is what? Is something of the order of, well, if 1 is out, then this term is almost 0 because of the correlation. Because 1 term, so if you take the expected value of 3 terms with numbers near 0 and 1 equals to million, is something of the term of the q to the power of million. So it's small. Of course, you need to estimate, but let us, so trust me, exponent trumps every this polynomial counting for all of this. Then there are terms where we have 2 pairs. So there are if there are omega, so G1 close to G2 close to G1 and G3 close to G4, and then this product of 4 can be split approximately into the expectation of products of 2. And when you study the expectations of product of 2, you have just this sigma f. And if you have, for example, a pair and 2 distant, so there are 3 groups, then these distant terms, again, each individual distant term just straightforwardly says that this is negligible. And so the only important products, if you take the larger k now, not k equals 4, but k equals something, is when these j's are close to each other. So there is a pair of close pair, then we have some gap, then we have another pair, then we have again gap and some another pair and so on. And only these terms are important, because for such a term you have what? First of all, how many of them? If k equals to 2l, then the number of such terms is n to the l times the element of plus this weight times this weight. So this is 1 over square root of n to the k. And so we have that these terms make some real impact. And this impact is in fact just this product of well, let's see, it is this sum of variances. Well, in this term. Well, further, there are more delicate terms. When you have some j's that are the same, and then the remaining that goes in pairs. this corresponds to the product of this term times the variance of f to some power. Of course, here I should, if I want to get a detailed proof, I should figure out every constant that f is this the coefficients before the sums are the same and everything works. But I guess at least in terms of in this hand waving terms, we have the same. We have exactly what we needed. Well, of course. I guess I have somewhat explained to you why do we have this tendency, at least when you consider a formal series. When you just say that for the formal series, you have these conversions. Because left-hand side and right-hand side is just a formal series in lambda, and you can compare its two halves. Nevertheless, there is a question of convergence. In fact, what you have done, what was done here, is that you prove that all moments of this random variables tends to the moments at the right hand side. And I guess that this can also be somewhat estimated. So you can estimate that not only when you decompose this sum into something how to say it. In fact, this discussion of the coefficients can be retold as an estimate. Again, the idea is the same. You have to now to say that if you have, say, a gap, a large gap, then you have an independence, or in a more delicate situation, you have an expectation of one part, is expectation of another part, times this, so the series of this sort. It seems that I cannot go into greater details because so there was a mistake and have no other time to correct it and to make the exact proof. But I guess I have explained you that these terms, at least it is possible that they are exactly either cancels out or are negligible, and the remaining terms makes this. Well, so I guess I want to stop here, and if there are no more questions, I will. So our course will end here. Okay. Then goodbye. Yes, Fedor, do you have any questions?
I have a question about final exam. That will be sent by
mail.
Which I sent with Google form. Yeah.
Yes, I guess I will use both methods. First, there are what was sent via Google form, and second, I have the list of participants from HSE, and then I can just send by their emails at edu HSE, just their corporate emails also. And if you want to send to some other address, you can just write an email to me, and I'll respond with the problems. Okay.
Okay.
Then thank you and goodbye.